All right, let's dive into a term that gets thrown around all the time, but can feel a little fuzzy. Software engineering. What does it actually take to engineer the software that pretty much runs our entire world?
I mean, think about it. We're surrounded by incredibly complex software every single day, from the apps on our phones to the giant systems that run our banks and hospitals. But how does a simple idea turn into a reliable, secure piece of tech that millions of people can use? Well, it's definitely not magic, and, it's a whole lot more than just writing code. It's a true engineering discipline.
Okay, I know, that sounds a little textbooky, right? But the key words here are everything. Systematic, disciplined, and quantifiable. This is the core idea. We're not just trying to hack something together that kind of works. We're applying proven engineering principles to build software that's efficient, reliable, and, this is crucial, maintainable for years. It's really the difference between building a simple shed in your backyard versus constructing a skyscraper. And of course, not all software is built the same way. We can pretty much put it into two big buckets. On one side, you've got your generic products. Think Microsoft Word or Adobe Photoshop. These are sold on the open market for anyone to use. But then you have custom software. This stuff is built for one specific client with a very specific job to do, like that MenCare system from our source material, which was designed from the ground up just for managing mental health patient records.
So, how do engineers actually get these systems built? Well, it turns out there are two major philosophies, two main schools of thought that have really shaped the entire industry. And they represent this fascinating tension between planning everything out versus being able to adapt on the fly.
And here's the fundamental difference. Plan-driven development is exactly what it sounds like. It's like building a house from a super detailed blueprint. Every single requirement, every design choice, it's all figured out before a single line of code gets written. Agile development, on the other hand, is much more like sculpting. You start with a general idea, you build a small piece of it, you show it to the customer, get their feedback, and then you refine it over and over in these short, quick cycles. This right here is the classic plan-driven approach in action. It's called the waterfall model. It's a very strict, linear process. You gather all the requirements first, then, once that's done, you complete the entire design, then you implement. You see how it works? Each phase has to be totally finished before the next one can even begin. It's super structured, but you can probably already see the potential issue. What happens if the requirements change halfway through? Now, let's flip over to the Agile way of doing things. Instead of massive 100-page documents, Agile teams use something called user stories, which are just simple, plain language descriptions of a feature from the user's point of view. They practice continuous integration, which just means everyone on the team is merging their code changes together constantly to catch problems early. They're always refactoring to keep the code clean and easy to change, and they use test-first development, writing tests before the code to make sure quality is baked in from the start. The whole game is about speed and being able to adapt. But here's the thing. In the real world, it's almost never a battle of one versus the other. Most big, complex projects end up using a hybrid approach. They'll do enough planning up front to make sure everyone's heading in the same general direction, but then they'll actually execute the work using agile methods so they can stay flexible and react when things inevitably change. So, regardless of the process you're using, any software that's even moderately complex needs a solid foundation, a solid structure. And that brings us to the absolutely crucial role of software architecture. I love this quote because it just nails it. The architecture is the skeleton, it's the high-level plan, it's not about the nitty-gritty details of the code. It's about the fundamental organization of the whole system. What are the big pieces? How do they talk to each other? If you get this part wrong at the beginning, the entire system can become brittle and just a nightmare to change later on.
A really common architectural pattern is this layered architecture you see here. The best way to think about it is like the floors of a building. At the very top, you have the user interface. That's what you, the user, actually see and click on. Below that, you've got layers that manage the UI and handle the core application logic. And then way down at the foundation is the system support layer, talking to the database and the operating system. The golden rule here is that each layer has a specific job and only talks to the layers right next to it.
So to make that less abstract, let's see how it works in practice. If we look at that MintCare system again, you can see exactly which parts live on which floor of the architecture. The UI layer is all about the forms and menus. The application layer below it is what's actually handling patient information and prescriptions. This separation is what makes the whole thing much easier for engineers to understand, build, and maintain over time.
Okay, let's shift gears a little, because for some systems, making a mistake isn't just an inconvenience. It can be catastrophic. And this is where we need to talk about dependability, which is really just a measure of how trustworthy a system is. This is the cautionary tale that every single software engineer learns about. The very first launch of the Ariane 5 rocket ended in this massive explosion just 37 seconds after liftoff. And it was all because of a software bug in the guidance system. And here's the truly terrifying part: the backup system had the exact same bug. It is just a brutal reminder of why dependability is so critical when the stakes are this high.
So, what do we actually mean by dependability? Well, it's not just one thing. It's really a bundle of 4 key properties. Availability. Is the system up and running when you need it? Reliability. Does it consistently do what it's supposed to do? Safety. Is there any chance it could cause harm to people or the environment? And of course, security. Can it protect itself from attacks or accidents?
But, and this is a huge but, achieving that perfect level of dependability costs an absolute fortune. As this chart shows, the cost to find and remove bugs goes up exponentially. Getting rid of the first, say 90% of faults, is one thing, but finding and fixing that last elusive 1%, that can cost more than all the other fixes combined. This is the economic tightrope that software engineers and businesses have to walk every single day. Okay, finally, it's so important to remember that software never, ever exists in a vacuum. It operates in the messy, complex world of people and company rules and business needs. This leads us to this fancy-sounding concept called a socio-technical system. But all it really means is that the system isn't just the code. It's the whole package: the hardware it runs on, the people who use it, and the official and unofficial rules and processes that surround it in an organization. All of these pieces are tangled up together. And this is the bottom line. A system can be a technically perfect, flawless piece of code and still be a total failure. Why? Because if it's too confusing for people to use, or if it just doesn't fit with how the company actually does its work, people will find a way to work around it, or they'll just reject it entirely. The human side of the equation is every bit as important as the technical one. And that brings us to a final, pretty heavy question to think about. We've seen how complex this all is, and we know about the economic trade-offs. It's practically impossible to ship any complex software with 0 faults. So what is the ethical duty of the companies that build and sell it? When something goes wrong, where do we draw the line on who is responsible? That's one of the biggest questions for our modern software-driven world. Thanks for joining me.